In this video, I am going to work these 4 Laurent Series example problems. Before I work these problems, I am going to go over this overview slide from our last video when we talked about Laurent Series, and I'm hoping to make this review about 5 minutes. The Laurent series is an expansion of the Taylor series that allows us to approximate any function f of z with a polynomial. For a Taylor series, the function needs to be analytic. For a Laurent series now, we can consider functions that might have a singularity at z naught. The formula for the Laurent series expansion of f of z is equal to the summation of coefficient an times z minus z naught raised to the nth power plus the summation of coefficient b sub n over z minus z naught raised to the nth power. The formula for the coefficient a sub n is here, which is 1 over 2 pi I closed curve integral c of f of z dz over z minus z naught n plus 1. And then our coefficient b sub n formula is over here, which is 1 over 2 pi I closed curve integral of c f of z dz z minus z naught minus n plus 1. In our formula for the coefficients, you can see how the singularity at z equals z naught might give us problems where the function's analytic and we cannot do this integration. So what we do is we surround our problem point, our singularity z naught, by a very small circle with radius r1. Again, r1 can be infinitesimally small so that it really only contains the point z naught. And then we take another circle of radius r2 that will enclose our curve that we want to integrate around. So C is our positively oriented simple closed contour around z naught that lies completely where the function is analytic. In other words, it lies between the two circles of radius r1, which surrounds z naught, and r2, which encloses C. In reality, we're going to try to avoid doing these closed curve integrals to calculate an and bn. We'll be using other techniques that we're going to cover over here. But one other point before we get to that, our Laurent series is composed of 2 parts. The first part, where the powers or the exponent on z minus z naught is positive, that's the analytic portion, and it corresponds, it's exactly the Taylor series expansion of our function. And then the second part is the principal part, where the exponent on z minus z naught is negative. Our first example of a Laurent series takes the Maclaurin series, which is just a Taylor series centered at 0, Ez, which is equal to the summation z to the n over n factorial, and we replace z by 1 over z. Because this formula is good for any complex number z, it's also good for the complex number 1 over z. So we have e to the 1 over z, our summation. Now we're going to have the 1 over n factorial still, and our z to the n is now replaced by 1 over z to the n. So this is our new Laurent series. And when we expand it out, we see that this part here is purely principal. There's no positive powers of z here. As I had mentioned, we are actually going to try to avoid these integral formulas for calculating an and bn. What we are going to do instead is rely on these 1, 2, 3, 4 formulas we have, our known formulas for e to the z is equal to the summation z to the n over n factorial. 1 over 1 minus z is equal to the summation z to the n when the modulus of z is less than 1. Sine of z is equal to the summation negative 1 to the n, z to the 2n plus 1 divided by 2n plus 1 factorial, and cosine of z is equal to the summation negative 1 to the n, z to the 2n over 2n factorial. And what we are going to do is when we want to find a Laurent series expansion for a function, let's say e to the 1 over z, for example, we're going to see which one of these 4 formulas most closely match our desired function. In this case, it looks a lot like e to the z. So what we will do is one of these 4, or maybe a combination of these 4 techniques to change this formula, e to the z equals summation z to the n over n factorial, so it looks like e to the 1 over z. And here, the simple thing to do is to replace this z with 1 over z, as we had in this example. Other techniques or other things we can do is multiply the entire equation by a value. So we can multiply both sides of this equation by a single value. We can do term by term differentiation. And we had an example of this when we did Taylor series, when we derived the cosine formula from the sine formula. And the last thing is we can make adjustments to summation indices. Our very long example in our last video was to find the Laurent series expansion of f of z equals minus 1 divided by z minus 1, z minus 2. And we can only fit part of this problem, 1/3 of this problem, on this overview slide. So we'll just look at it really quickly. First, because this f of z does not look like sine or cosine, we didn't use these two. It doesn't look like e to the z. It looks kind of like 1 over 1 minus z, and that it's a polynomial over a polynomial. First, we broke down this fraction using partial fractions to rewrite f of z is equal to 1 over z minus 1 minus 1 over z minus 2. The other thing to note is that f of z has two singular points, z equals 1 and z equals 2, which means now we need to divide our domain into d1, where z is less than 1, d2, where z is between 1 and 2, and d3, where z is greater than 2. And by dividing it up into these three areas, we avoid our singular points, where z equals 1 and z equals 2, and at the same time we cover our entire rest of the plane. So we have the entire space where the function is analytic. For this overview slide, we only looked at d1. So for the modulus of z less than 1, first we look at the first part of the partial fraction, 1 over z minus 1. We can get it into this form over here of 1 over 1 minus z by multiplying the top by -1 and the bottom by -1. We factor out the -1, and what's left is 1 over 1 minus z, so we can plug straight into the formula summation of z to the n. The only thing we need to check now is that the modulus of z is less than 1, but that is true in d1, so we're good here. Next, we look at the fraction 1 over z minus 2. In this case, we want to convert this to the form 1 over 1 minus z. So this is a 1 combined with z, not some random number or constant 2. So we can factor out the 2, and in fact we're going to factor out the -2, so that we get our minus 1/2 times 1 over 1 minus z over 2. So this is algebraically equivalent to 1 over z minus 2, but now we have our 1 over 1 minus z over 2 in this form here, where we replace the z with z over 2. So we have our -1/2, and now we have our summation of z over 2 to the n. And then again, we need to verify that what we replace the z with, that is the z over 2, is still less than 1. And that is true when modulus of z is less than 1. This fraction will also be less than 1, so we're good. So now we can write f of z is equal to 1 over z minus 1 minus 1 over z minus 2, plugging in minus summation z to the n for 1 over z minus 1, and also plugging in this summation for 1 over z minus 2. But we also have this negative, so this becomes a plus 1/2 summation z over 2 to the n. And this is good for d1. That's our quick overview, so now let's go through the other problems. We will start with this first problem. Expand f of z equals 1 plus 2z squared over z cubed plus z to the 5th. The first thing to do whenever you have a polynomial over polynomial is to always simplify this fraction as much as possible. So I'm going to start with my 1 plus 2z squared over z cubed plus z to the 5th, and I'm going to separate this out into two fractions. I have my 1 over z cubed plus z to the 5th, and then I have my 2 over z squared over z cubed plus z to the 5th. Now I can factor out my z cubed here, so I get 1 over z cubed, 1 over 1 plus z squared, right? My z cubed is fine. If I'm centering around z equals 0, this just becomes another z to some exponent, which we'll combine in later with our summation. Here, same thing. I can factor out my 2z squared and a z cubed, and then what I'm left with inside is 1 over 1 plus z squared. Again, this then can simplify. It's just going to be some power of z that we multiply our summation by. In both of these terms then, what I'm working with is 1 over 1 plus z squared. In other words, I'm going to use this formula here. I'll circle in blue, and I will copy it down here. 1 over 1 minus z is equal to the summation of z to the n, and I'm going to replace this z here and this z here with minus z squared. And when I do that, I'm going to get then 1 divided by 1 plus z squared is equal to the summation minus z squared to the n. In terms of my f of z, that means I'm going to have my 1 over z cubed summation then. Here I went ahead and took out the negative 1 to the n. I separated that out, and then I'm left with z to the 2n. For my next term over here, I still have my 2z squared over z cubed, which this simplifies to 2 over z, and then summation, again, I take out my negative 1 to the n, and then I'm left with z to the 2n. We can definitely simplify this a little bit algebraically. What I did is I factored out the 1 over z cubed plus 2 over z, and then I expanded this out here. So I have n equals 0. I'm going to get 1 times z to the 0, which is also 1. When n equals 1, I'm going to get a negative and then z squared. When n equals 2, I'm going to get a positive and then z to the 4th. Then my signs alternate, so negative z cubed plus z to the 8th. Then next I multiplied 1 over z cubed by this series here, and then I multiplied 2 over z by this series as well. I added my like terms to get my final answer. The next problem is to expand h of z equals z times cosine of 1 over z. In our problem h of z equals z cosine 1 over z, this kind of obviously looks like we're going to be modifying this cosine z formula. And what we're going to do in particular is we're going to substitute then 1 over z for z in this formula, which I've recopied here. Cosine z is equal to summation negative 1 to the n, z to the 2n divided by 2n factorial. So in other words, we're going to modify this formula so it's cosine of 1 over z is equal to summation negative 1 to the n. We still have our 1 over 2n factorial, but now this z is replaced with 1 over z raised to the 2 over n. Now our h of z, we still have this factor of z, but for cosine of 1 over z, we're going to replace that with our summation formula. So that's summation n equals 0 to infinity, negative 1 to the n, 1 over z to the 2n, 2n factorial. Writing out a few terms, plugging in n equals 0, this becomes 1, this becomes 1, and this becomes 1, so we have 1. When n is equal to 1, we get a negative 1 over z to the 2 times 2, so that's negative 1 over 2z squared. When n is equal to 2, we get a positive, and then we have z to the 4 times 4 factorial. When n is equal to 3, we get a negative 1 over z to the 6 factorial. And finally, multiplying our z in, we get this form here, this pattern, z minus 1 over 2z plus 1 over 4 factorial z cubed minus 1 over 6 factorial z to the 5th, and the pattern keeps going. These are going pretty fast. Actually, this one's going to take a while. We have to divide up our domain into 3 areas. But anyway, this third problem, find the principal part and the residue, that is the b1 coefficient over here, of f of z equals z cubed plus z squared over z minus 1 squared at z naught equals 1. And we want to note now we're centering our expansion, our series, at z naught equals 1 instead of z equals 0. All our other formulas for e to the z, 1 over 1 minus z, and sine z and cosine z are all centered at 0. So we need to take that into account. So remember when I said the first thing to do is simplify your fractions? I guess I lied. Here we need to work on getting everything centered first at z naught equals 1. You will notice that the denominator, that 1 over z minus 1, this is already centered It's already of the form z minus z naught, where z naught is equal to 1. What we need to work on is expanding the numerator, z cubed plus z squared around z naught equals 1. And the thing that will make your life so much easier is to notice that z cubed plus z squared is analytic. So this can be represented by a Taylor series. Here I have the formula for the Taylor series coefficients. A sub n is equal to the nth derivative of f evaluated at z naught divided by n factorial. To use this formula, first we're going to evaluate f of 0, that is the function at z naught, where z naught is equal to 1. So the function evaluated at 1 over here, z cubed plus z squared, is going to be equal to 2. The first derivative now of f is 3x squared plus 2x, evaluated at 1 is equal to 5. The second derivative now is 6x plus 2, evaluated at 1 is equal to 8. So now we can write our coefficients. A naught is equal to f of 0 of 1 divided by 0 factorial, which is just 1. So that's going to give us 2. A1 is this 5 divided by 1 factorial. That gives us 5. A2 is this 8 divided by 2 factorial, which will give us 4. That means our Taylor series expansion is our first coefficient is 2, where we have z minus z naught raised to the 0 power. Our second coefficient is 5, z minus z naught raised to the first power, plus our next coefficient is 4, z minus z naught raised to the square, and you can continue this pattern. But these are the first few terms of our Taylor series expansion of z cubed plus z squared centered at 1, as opposed to being centered at 0. To finish this problem off, then f of z is our z cubed plus z squared divided by z minus 1 squared. So I'm going to go term by term dividing z minus 1 squared. So here, this is just 2 divided by z minus 1 squared. Here when I divide 5 z minus 1 by z minus 1 squared, these cancel and I'm left with z minus 1 on the bottom and 5 on the top. Here, on my next term, I'm left with 4, and this z minus 1 squared cancels with the z minus 1 squared on the bottom, and I can continue my pattern, except I didn't calculate any more coefficients, so we'll just put dot, dot, dot. Coming back over here, looking at our problem, it was to find the principal part. So the principal part is the part with the negative exponents, and you can see this right here, these two terms are the ones with the negative exponents. This is the principal part. And you can see from here on out, because now you're going to get z minus 1 to the cubed, from here on out you're going to have analytic part. So this is the sum total of the principal part. And then also, we wanted to know the residue, the B1. That's the coefficient that goes with the z minus z naught raised to the 1. That's this coefficient 5. So the residue is equal to 5. This residue here hints at what we will be doing in future chapters when we're integrating. We're going to be using Cauchy's integral theorem to integrate, and to do that we'll need to be finding residues. And that's what all of this work with the Laurent series and Taylor series is about. It's leading up to finding residues. Our last problem is to find the Laurent series expansion for r of z, which is equal to z plus 2 divided by z squared minus 5z plus 4. The first thing to do when we have this polynomial over polynomial and we're not trying to center it somewhere other than 0 is we're going to simplify our fraction. Since this is an algebraic step, you might do this a different way. You might separate this into two fractions, z over z minus 4, z minus 1, plus 2 over z minus 4, z minus 1, and you could do something else very clever along the way. What I do, because I see this as z minus 4 times z minus 1, I want to separate out these two factors in the numerator, so I use partial fractions. So here I have z plus 2 divided by z minus 4 times z minus 1, and I want to separate this out as some constant a over z minus 4 plus some constant b over z minus 1. And the way I solve this equation, I multiply both sides of the equation, the left side and the right side, by z minus 4 times z minus 1. When I multiply this left side times z minus 4, z minus 1, these cancel out, and I'm left with z plus 2 on the left side. When I multiply my term with a by z minus 4 times z minus 1, the z minus 4's cancel out, and I'll be left with a times z minus 1. When I multiply this term with the b times z minus 4 times z minus 1, the z minus 1's will cancel out, and I'll be left with b times z minus 4. Now I'm going to multiply out my a times z minus 1, my b times z minus 4. I'm going to group my terms with z's and group my terms without z's. So my terms without z's, that is my minus a and minus 4b, that should equal to 2. My terms with z's, that is az plus bz, that should equal to z. When I solve these two equations, I'm going to get a equals 2 and b equals negative 1. And so I'm going to write that here. My z plus 2 over z minus 4 times z minus 1 is equal to a, which is 2 over z minus 4, plus b, which is minus 1. So I'm going to put my minus here over z minus 1. And the next thing to note is we are going to have singularities at z equals 1 and z equals 4. This means we're going to have to divide our domain up. Our domain now is going to be modulus of z is less than 1, modulus of z is between 1 and 4, and modulus of z is greater than 4. So here are our two regions, D1, which is the circle of radius 1, or the circle less than radius 1, the disk where we have less than radius 1. Our D2 is the annular region between the circles with radius 1 and radius 4, and D3 is all this information outside, or all the points outside the circle of radius 4. Again, we have two singularities that we need to avoid. We need to avoid the circle z equals 1. We need to avoid the circle z equals 4, so that will separate our domain into three distinct parts, D1, D2, and D3. And remember, all this trouble is for when we were calculating our coefficients using these closed curve integrals. In order to integrate, we needed to have the curves in some region that was analytic. We are starting with D1, and I'm just going to shade D1 in our drawing here. So D1 is this area inside the circle of radius 1. We are going to start with region D1, where the modulus of z is less than 1. We have these two fractions here to contend with. That's 2 over z minus 4, and the second part is 1 over z minus 1. When I compare these fractions to our known sequences, it doesn't look like we have an e to the z. We certainly don't have sine and cosine. So this is the formula here that we will be using. I'm going to start with 1 over z minus 1 because it looks so close to our formula 1 over 1 minus z. And in fact, if I multiply the top by negative 1 and multiply that by the bottom by negative 1, which is negative 1 times 1 over 1 minus z, so this is negative 1, and then plugging in for 1 minus z, our summation formula, summation z to the n. And this formula here is good when the modulus of z is less than 1, which is exactly the case in D1. So we're good here for this fraction 1 over z minus 1. We have a summation form, or more to the point, we have a polynomial form. I'm going to move our result down a bit to give us room to look at the 2 over z minus 4. That's the second part of our partial fraction decomposition. Again, I'm going to be using this formula, polynomial over polynomial. The first thing I need to do is get a 1 in the denominator. That's pretty straightforward. I can just factor out a 2, so I have 2 times 1 over z minus 4. Next, I'm going to focus on my 1 over z minus 4. When I compare it to this form here, what I want is 1 divided by 1 minus, and remember this z can be replaced with a simple function of z. So essentially, I'm going to focus on trying to get a 1. Over here, I can get a 1 if I factor out a z, or I can get a 1 if I factor out a negative 4. I have written what each of those cases will look like here. If I factor out a z from this denominator, I'm going to get 1 over z, and then I'm left with 1 minus 4 over z. You can verify if you multiply the z here, you'll get back your z here, and here you'll get back your negative 4. If I factor out a 4, so I take out a negative 1 over 4, and I factored out a negative 4 because I want a positive 1, I'll get a negative z over 4 plus 1. I almost always try to factor out the constant rather than the variable z, but not because it's the right thing to do or more often correct. It's just because somehow that seems more natural to me. But what's going to determine which one you use is you have to remember for this formula here, our modulus of z needs to be less than 1. So here, when we replace z with 4 over z, the modulus of 4 over z is greater than 1 because in d1, z is less than 1. Whereas over here, we have 1 minus z over 4, so when we replace this z with z over 4, the modulus of z over 4 will be less than 1 because z is less than 1. So that means this is the form that we will use. This is the form that will allow our series to converge. Now I have my 2 over z minus 4 is equal to 2. And then for the 1 over z minus 4, I'm going to substitute this expression here where I factor out the negative 1/4, and then I have 1 over 1 minus z over 4. The 2 and the minus 1/4 simplify to minus 1/2. The 1 over 1 minus z to the 4th, I'm going to substitute into my summation formula. I'm going to substitute z over 4 for z, so I'll get summation of z over 4 to the n. And I'm just going to repeat my note since I erased it here, that my z over 4 here is less than 1 because I'm in d1, and the modulus of z is less than 1. And this is what will guarantee that my series here, or this series here, will converge. Now I'm ready to write my f of z. I'm sorry, I guess it's r of z, but you know what? I'm just going to stick with f of z. Who calls functions r? But anyway, f of z is equal to 2 over z minus 4 minus 1 over z minus 1. Again, this is from partial fractions. And then my 2 over z minus 4 from this work is equal to minus 1/2 summation z to the 4th to the n. And then I need to subtract my 1 over z minus 1, so that will give me a plus over here, summation of z to the n. So this is my final answer for D1. I'm going to copy my answer up here so that I can clear the rest of this out and make room for D2. Next, we're looking at D2, where the modulus of z is between 1 and 4. So the picture of that is this annular region between the circles of radius 1 and radius 4. I'm going to borrow the work I did in D1 for the fraction 2 over z minus 4. I had factored out the 2 in the numerator, as well as factoring out the 4 from the denominator. And I have then my 2 times negative 4, and I did factor out a negative, which will give me 1/2. And then factoring out the 4, I have z to the 4th minus 1, but I did factor out a negative 4, so that becomes 1 minus z to the 4th. Plugging this in to my formula again, substituting z over 4 for z, I get the summation of z over 4 to the n. And then in this case, when I do my check that what I substituted for z here, the modulus of z over 4 is less than 1 because in this range, z, modulus of z is less than 4. So I'm good here, and I can use this substitution. It will converge. Similarly, I'm going to borrow the work I did in D1 for 1 over z minus 1. You know, in D1, D2, and D3, it's always the same fraction, so feel free to not redo all the work. Like, go back and look at your work. So I have 1 over z minus 1. Factoring out the negative 1, I get negative 1 times 1 over 1 minus z, which is negative, and then plugging this formula in, summation z to the n. But here, in D2, the modulus of z is greater than 1. So we cannot use this form this series will not converge. There are two ways then I could get this 1 here in front of the z. And I tried here by altering this 1 to become a -1. But what I could also do, instead of working with the constant, I could work with the variable. In other words, I can factor out the z in the denominator. So what I get is 1 over z times 1 over 1 minus 1 over z. And if I multiply this out, you can see the z times 1 gives me my z, and my z times minus 1 over z will give me my -1. Now I have my 1 over z, which is just a power of z. We can multiply that in at the end into the summation, but I have this 1 over 1 minus 1 over z. So I can substitute that in here, where I substitute 1 over z for z. So I'm going to get my 1 over z here, and here I'm going to substitute summation of 1 over z to the n. Combining now this 1 over z with this 1 over z, I get summation of 1 over z to the n plus 1. And now our goal, though, with this 1 over z minus 1 is to get a 1, a positive 1. And I tried to do that by changing this -1, the constant, into a positive 1, but that didn't work. So the other thing I can do, if I can't get something to work by working with the constant, I can work with the variable z. So I can factor out, or divide the denominator by z. So factoring out 1 over z, or dividing this by z, I get 1 over 1 minus 1 over z. So you can see if I multiply the z through, I would get my z term here. And then multiplying z times minus 1 over z, I would get my -1 term. So these are equivalent or equal. So now I have my 1 over z, which is just power of z, and I can fold it into my summation later. And then I have 1 over 1 minus z, which is exactly this form when I substitute 1 over z for z. So in other words, remember, I can substitute for z a simple function of z. My simple function is going to be 1 over z. So I still have my 1 over z here, and then for this 1 over 1 minus z, I'm going to have summation 1 over z to the n. Then I combined this 1 over z, I move it into my summation, and I get my summation 1 over z n plus 1. Of course, I still need to verify that what I substituted for z in here, that its modulus is less than 1. I substituted 1 over z for z, so the modulus of 1 over z is less than 1 because in D2, z is greater than 1. Now I am ready to write my solution for D2. So r of z, which is equal to z plus 2 over z minus 4 times z minus 1 by our partial fraction decomposition is equal to 2 over z minus 4 minus 1 over z minus 1. And then my 2 over z minus 4 is equal to minus 1/2 summation z over 4 to the n. And then I have a minus, and my 1 over z minus 1 is equal to summation 1 over z n plus 1. I'm going to move a copy of this over here so that I can clear the rest of my work out and make room for D3. D3 is the area of the domain where modulus of z is greater than 4, so it's everything outside the circle of radius 4. We are going to start again with our part of our decomposed fraction. So we have 2 over z minus 4, borrowing again from D2 because really these are the same two fractions you're working with. Don't redo all the work. So if I factor out the 2 first, and then I factor out the 4 from the bottom, when I plug this into my formula, I need to check that this z over 4 is less than 1, but it's actually greater than 1 when we're in D3, where z is greater than 4. So we can't use this formula. We're going to have to use the other strategy where we work with the variable to try to get the 1. Again, I factor out my 2, and now to get my 1, instead of trying to get my 1 by taking this constant and making it a 1, I'm going to divide by z to make this z into a 1. So I factor out my 1 over z, this becomes 1, and this becomes minus 4 over z. So I still have my 2 over z. I substitute 4 over z into my formula here, and I get the summation of 4 over z to the n. And now checking to see this 4 over z is less than 1, well, it is in D3 because z, modulus of z, is greater than 4. So we're good here. Next, I'm going to be working with the fraction 1 over z minus 1. Again, I try to factor out the minus 1 to get minus 1 over 1 minus z. In this case, my z is greater than 4 in D3, so I cannot use this form here. And that was by trying to work with the 1, the constant, and make it equal to a 1. So what I'm going to do is work with the z and make that equal to a 1. So in other words, I'm going to factor out my z, and I'm left with 1 over 1 minus 1 over z. In this case, I still have my 1 over z. When I plug in 1 over z into my formula, I get the summation of 1 over z to the n. Then combining this 1 over z, or moving this 1 over z into the summation, I get 1 over z to the n plus 1. Now I'm going to check that this 1 over z is less than 1, which it is, when modulus of z is greater than 4, which it is in D3. So I'm good here. Now I'm ready to write my r of z, which is z plus 2 over z minus 4 times z minus 1 by our partial fractions decomposition is equal to 2, z minus 4 minus 1 over z minus 1, and our 2 over z minus 4 is equal to, I did a little bit of manipulation here. I moved the z into the summation, but I still have 2 on the outside, summation 4 to the n, and now I have z to the n plus 1, and then I have minus, and then for our 1 over z minus 1, I have summation 1 over z to the n plus 1. So this is my final answer. And here are my final answers for D1, D2, and D3. I'm really glad we had a chance to do these 4 problems, especially these 3. They each had something new to look at. And this last one is just another example of dividing up our domain. I won't really review everything since really the point of this was just to go through those problems. So that's it for this video. Thank you for watching.